You see again, it makes some new strings because it's got a couple of pluses in there, the string that is passed into a val. And then it does a document write. And here you can see it adds a source of another JavaScript, and we'll tell you about that later. But this is the final result of that big paragraph of obfuscated code, is it's calling a val on this. Turns out this source downloads another JavaScript. It's another layer of indirection that tends to be used in these attacks. And it might bounce from server to server to server, but it's all over. At this point, it's been injected, and the browser is going to do whatever it says. You can't stop it at this point. Turns out what this particular one did was keep getting an ad, kind of a spyware, adware kind of thing injected into the page, and it was an ad for a Spanish-speaking adult friend finder kind of site. And as we'll see, a lot of ad servers and malicious software use the same. They have a very similar fingerprint and a very similar methodology in the way they're going about things, which we'll talk about some more later. So to address the pitfalls in the current technology while we did this, there's been some other great projects that we've built on or heard about through the grapevine. And this sort of monkey technology has been going on for a little while. The MS Strider project was kind of the first honey monkey project that I really heard about anyway. There might have been some other things before, but they had some really great results. They scoured the web looking for O-Day exploits. There's not a lot of info on the project, but from what I hear, they've had very successful results and patched a lot of bugs and vulnerabilities in Internet Explorer and other tools due to that. Other one, MITRE has a honey client that they're using, Capture, Honey C. They're all fairly similar, written by different groups for different purposes, but kind of have the same functionality in the end. In general, these tend to be very heavyweight and resource intensive, whether running VMwares or starting up numerous different browsers and running through all the different versions. And that tells you a lot. It tells you a whole lot, because if you're running it in the browser, you're going to see. But at the same time, with simple behavioral analysis, you're going to be bypassed by some other things. Say if the malicious code is date sensitive. If you run it on Tuesday, are you going to have the same functionality as on Wednesday? So then you get into a lot bigger bloat of what would actually be happening, because you're going to have to actually change the system clock, and you can't do that for every conceivable thing. So you really have to go at a deeper level to get the full understanding of what's going on. Now that technique's not used a lot, admittedly, but it could be, and there's other similar techniques that could happen like that also. Also tends to be very high interaction. Some of these techniques also have to be high interaction. Lots of human time, lots of loading up the VMs, lots of running it through. Human analysis, time consuming. Very, very time consuming. I don't know how many of you have ever dealt with malicious JavaScript or malicious code in general trying to figure out what it does. It's very error prone. You take a lot of time running through the various layers of the scripts, the onioning as known. And it's not that safe. As we mentioned earlier, you have your text area wrapper under O-Day conditions. They're probably going to be closing up that text area whenever they're running the script. And then you get stuck doing the same thing. So now we're going to talk about what we found.
So we've talked about the web crawler component, and our idea was to basically try to find some interesting samples of JavaScript content from the wild. And our first target was MySpace. It's a very popular social networking site I'm sure you're all familiar with. For the MySpace run, we captured about 8 gigabytes of data over about 3.5 days. Like I said earlier, we captured about 400 or 500 unique JavaScript documents that were identified by their MIME type. Some other crawler runs that we performed with the hope of finding some interesting samples was serial number or software cracking or whereas sites. Using a little Google hacking, we were able to identify a large collection of .edu servers that had been compromised and were hosting pornography as well as Trojan downloaders. After we discovered that, we decided, well, let's look for some military sites that had been compromised. And being good American citizens, we only looked at other nations' military sites. And basically, we found just some simple Google hacking that you could find a number of compromised .mil, .country code sites that were hosting pornography or Trojan downloaders, things of that nature. And then also the good guys at stopbadware.org have an extensive list of bad news websites, compromised web servers, Trojan downloader hosts, all sorts of places you really want to avoid. But it's a great resource for the security researcher because the work is really done for you. You can go to that group and get great lists of all sorts of malicious sites. And now I hear that Google is releasing more information on their lists of malicious sites that they've identified and that they block through their search technology. And so we're always happy to see some more information sharing from other organizations helping to identify the bad guys. So what we found is that, talking mostly about the MySpace run, is that there's lots of obfuscation out there. But most of it was essentially benign. Adware, ad syndication, cookies, hit trackers, Google Analytics. These are all sorts of things that use dynamic scripting. They were all over the MySpace pages we spidered. And, but in a sense, they're really benign. They weren't actually trying to exploit your browser. They were more trying to make sure that you had to consume their advertisements. So MySpace, at least based on our result, they run a fairly clean ship. In our 400 or 500 JavaScripts, we did not identify any as being clearly malicious. They were obfuscated, they were evasive, but mostly for functionality such as displaying advertisements or tracking your path through various commercial websites. So how do you use this information to identify or to classify good and bad JavaScripts? So our approach, as Daniel showed you, basically we instrumented the SpiderMonkey interpreter. We wrapped and logged a lot of key functions such as object instantiation, string concatenation, uses of escape and unescape, uses of character functions, things of that nature. So with these logs, basically we could generate statistics about the usage and essentially the execution profile of these JavaScripts. How many strings were created during execution? How many objects were instantiated by name? How many document write calls were made? Those kind of things. So we really started looking at trying to fingerprint what kind of ratios or relations between those function calls or those behaviors would indicate a script that's trying to do something bad or untoward, or versus something that is essentially benign, but maybe trying to obscure its purpose. So this first graph, I apologize if it's hard to make out the titles here. Basically, these are 4 samples, Monkey Chow 1 through 4. And these are 4 samples of malicious JavaScript. And what you're looking at is basically at the very bottom is number of calls to document.write. The next stack above that in the reddish maroon color is basically string instantiations. And because string instantiations are so frequent, we really had to scale those by a factor of 50 to yield graphs that really show anything. You've got calls to eval, you've got element instances, you've got, and at the very top of the stack is object instantiations. So what we're seeing is that string instantiations are very frequent in these malicious JavaScripts. They're creating new strings all over the place. And we believe that's partly a reflection of the use of the string splitting technique we showed earlier, and that the authors of these scripts are being evasive about the actual string content within their scripts. They're adding these strings or encoding them together and creating string instantiations. And also point out that one reason we have so many string instantiations is the plus operator really instantiates 2 objects. Any Java programmers out there will tell you that's the downfall of using string concatenation. So we're seeing a lot of these string instantiations.
I had a question over here before we.
Are you using static counting? You're counting like the number of document writes in the document?
This is as it gets evaluated. So it's not just going through and counting the text. It's actually, it's going to output one document write for each time in that loop that it's actually called.
The question was, are we just simply counting the seeing document.write in the syntax of the script? And the answer is no, we instrumented the interpreter so that, for his example was, if you have a loop and you're calling document.write, well, we'd see 50 document writes if that loop went through 50 times. Whereas if you're simply inspecting the syntax of the script and without understanding that it's in some sort of loop structure, you would see, yes, the string document.write appeared once in this script. So just to make the point, we're wrapping and logging a lot of the internals of the interpreter here with the idea of that's a good place to insert yourself if you're really trying to look at the behavior of the script instead of the syntax or the semantics of it. So we're going to look at samples from MySpace, the run. And along the bottom, we've broken it down by domain, host.top-level domain. And as expected, when we spidered, starting at the MySpace homepage, the top domain for number of unique JavaScript documents collected was the myspace.com domain. There's a few interesting things that showed up in there. Photofile.ru is the fifth down. So clearly there's a lot of Russian photo hosting going on MySpace. And then interesting to round out the top 10, there was a tie, so really we had 9, is HillaryClinton.com, which was apparently lots of links to that site through MySpace, and there's a good there's several JavaScripts that are hosted there that you will find if you spider MySpace. So to point out, obviously the number of document writes are a lot higher in proportion with these benign samples in terms of in relation to the other function calls. In the next graph, we're really going to put them side by side. And so the 4 samples on your left are known bad JavaScripts that we identified. The other samples are the collections from MySpace. And what we're seeing as a trend is string instantiation is relatively more common in malicious JavaScripts than it is in benign ones. Also, what we see is that document write calls are relatively more frequent in a benign JavaScript than they are in a known malicious JavaScript. So to speculate on why that might be, a lot of these commercial or benign JavaScripts, they offer a lot of functionality. They're writing out elements to part of the page. They're writing out various HTML content. And so you'll see document write called throughout the script in various functions. However, in the malicious case, typically the author of the script will build up his payload using string instantiations, and then eventually do a lot of times just a single document write of a variable containing their payload, whatever it is, be it shellcode or one of the month of browser bug kind of exploits. And so just really visually, you can see there's really something different here. And then another interesting point is that object instantiation is relatively more popular in the malicious scripts. So what we're seeing, for whatever reason,